Hello and welcome to this video where we're going to be going through the questions on the Haber process on page 81 and 82 of the separate science chemistry booklet. Let's get started. So we start off with a 6-mark question. It tells us that ammonia is manufactured from nitrogen and hydrogen by the Haber process, and it gives us the formula. It tells us that the forward reaction is exothermic, and it gives us the conditions that are used: 200 atmospheres of pressure, 450 degrees Celsius, and the presence of an ion catalyst. We need to use our equation and our knowledge of reversible reactions to explain why these conditions are used. We must consider both the yield and the rate of reaction in our answer. When thinking about our 6-mark questions, it's always worth thinking about the format. You can see that they've given us 3 points. So if we can make 2 valid points about both the yield and the rate of reaction, according to each of these points, then we're going to pick ourselves up 3 marks. So let's start off with the pressure. Now the pressure is high pressure, and that will increase the rate of reaction. That's because over here we have 4 molecules, 1 nitrogen and 3 hydrogens, whereas over here we only have 2 molecules of ammonia. So increasing the pressure will shift the equilibrium towards the side with the less number of molecules. However, high pressure vessels are expensive, so the pressure cannot be increased too much, otherwise it will outweigh the cost. Next, let's think about the temperature. It tells us here that the forward reaction is exothermic, and therefore we would want low temperatures. To increase the yield. However, the rate of reaction would be too slow if the temperature was too low. So a compromise solution has to be met. And finally, we've got the presence of an ion catalyst. Catalysts will speed up the rate of reaction. They also allow lower temperatures, which will make it much more cost effective, as you'll need to waste less energy heating the reaction up. Question 2. In the Haber process, the forward reaction is exothermic. Explain in terms of bonds why this reaction is exothermic. Well, firstly, energy is required to break the bonds in the nitrogen and hydrogen. Because it's exothermic, this is less than the energy released when bonds are formed in ammonia. So our 3 marks will come from the idea of the energy required to break the bonds being less than the energy released when bonds are formed. Let's have a look at the next question. Complete and label the reaction profile for the Haber process. Include the energy level for the product and the energy change for the reaction. Well, we know that this is an exothermic reaction, which means that energy is released, and therefore the energy level of the products will be lower than that of the reactants, and so will look like this. The energy change will be the change from the reactants to the products, so this bit here. Remembering to label on our products of our reaction here. Question 4. Use the balanced symbol equation for the Haber process and the bond energies given in the table below to calculate the energy change for the forward reaction. So when we're doing this, our reaction is nitrogen reacting with hydrogen to form ammonia. When doing these questions, we want to split the equation in half. Let's think about the reactant side. Firstly, here we need to break this nitrogen bond, which is 916, and there's only one of them. Here we need to break the bond between the hydrogens, which is 436. But this time, we've got 3 lots of bonds to break, so it'll be 3 multiplied by 436. So 916 plus 3 multiplied by 436 is going to give us 2,224. If you got that number, you'd be picking up 1 mark. We then need to work out this side, on the ammonia side. So here we've got NH3. So there are 3 bonds between the N and the H. So there's 3 lots of this 386. But we've also got 2 lots of those molecules. So in fact, we've got 3 lots of 2, which is 6. 6 multiplied by 386 gives us 2,316 kilojoules. To work out the energy change, we want to do the energy put into break bonds minus the energy released. So 2, 2, 2, 4 minus 2, 3, 1, 6 gives us minus 92, and that's our answer. Not forgetting the minus, because of course it's an exothermic reaction. Okay, this last one's quite tricky, linking into the quantitative chemistry topic. So in 1909, Fritz Haber demonstrated his method to make ammonia on a laboratory scale. He could make 125 centimetres cubed of ammonia per hour. Using this rate, calculate the mass of ammonia that he could make in 1 whole day, assuming the volume measurements were taken at room temperature and pressure, where 1 mole of gas occupies 24 decimetres cubed at room temperature and pressure. So the first thing we need to think about is the fact that he can make 125 centimetres cubed per hour, which we've taken from here. Now we're asking how you can make in a whole day. And a whole day is 24 hours. So therefore you can make 125 multiplied by 24 centimetres cubed, which is 3,000 centimetres cubed per day. We then want to turn our 3,000 centimetres cubed into decimetres cubed. To convert into decimetres cubed, you divide by 1,000. So 3,000 divided by 1,000 gives us 3 decimetres cubed. We then want to use our equation. The number of moles equals the volume in decimetres cubed divided by 24, which will leave us 3 over 24 for the moment. Finally, to work out the mass equals the number of moles multiplied by the relative formula mass of ammonia. So the relative formula mass of ammonia, NH3, we've got 1 nitrogen which has a mass of 14, we've got 3 hydrogens which have a mass of 1 each. Adding that up gives us 17. So now we can substitute our numbers into the equation. So mass equals the number of moles, which is 3 over 24, multiplied by the relative formula mass, which is 17. And if we work that out, we get 2.125 grams to 3 decimal places. Hopefully you understand those questions a little bit more. And as always, happy sciencing.